Hello guys, it's Ert here, and today will be the first episode of a new series that's going to be on this channel, Rewriting Physics. We're going to be looking at different equations and different concepts in physics that seem to line up with each other and testing those out with their SI units and creating a new notation for those concepts according to their units. So with that being said, let's start off with finding the bases of the system and looking at the differential equations for a mass on a spring versus the differential equation for electromagnetic circuits, so capacitors, resistors, inductors, and also at the energy formulas for, work equals force times distance, and the potential energy being charge times voltage. So the way we'll start here is firstly, you'll notice that I am using alpha here for acceleration. If I can click. I'm using alpha here for acceleration. And I do cross my D's for derivatives, but alpha being used for acceleration will be consistent throughout the series. I'm making sure to not use A because A is for area. And A can also be sometimes used for action, which we will discuss in a much, much later episode. So, with that being said, let's get started. Starting off, we first look at the units for voltage. And volts are kilograms times meters squared per second squared coulomb squared. No, per second squared coulomb. Per second squared coulomb. And we will immediately notice that work and potential energy, which are both just work is the change of energy, and potential energy is just energy. So basically, energy already has units of kilograms times meters squared per second squared, and force has units of kilograms times meters per second squared, of which I will write in this way. So that is force. I know this is being done in opposite directions, whatever. But we recognize that all I did here was replace coulombs with meters, and everything worked out. And that, in fact, is not a coincidence, because what we want to look at is, let's start with inductance. Okay, inductance has units of kilograms meters squared per coulomb squared. And the reason we're not using amperes here has kind of become obvious because of voltage, but inductance is that. And if we look at mass, yes, I'm using a capital M. Let's not worry about that for now. It doesn't really do much anyways. Mass is kilograms, but we can also write that as kilograms times meters squared per meter squared. Again, seeing the coulombs being turned to meters, meters cancel out, and you get mass. The resistance has units kilograms meters squared times seconds coulomb squared. And guess what the units for drag are? Kilograms per second. And of course, we can go times meter squared, all that. So that's drag. The spring constant is kilograms per second squared, which again, I'm going to write as this. And I think you already know what to expect with capacitance. Inverse capacitance has units of kilograms times meter squared per second squared times coulomb squared. Now, if we were using amperes, we would get kilograms meter squared per second squared ampere squared. Then this would be per seconds cubed ampere squared. And this would be per seconds to the fourth ampere squared. But we're using coulombs instead. And of course, we will also notice that multiplying voltage by charge is just this. The C's cancel out and we get energy. That works. And of course, meters times, well, the meters here from distance also cancel out and you get energy there too. So now, with that being said, we can now just join these differential equations into one. So force of some unit is mass of some unit times acceleration of some unit plus resistance times the velocity of that unit. Let me change that up a little bit. Plus some other value which we will call gamma for now, times the unit itself. And I should also mention that later on we will recognize F equals QE as, well, the force equaling Q times the electric field as something that can also stem from this formula. Let us now just check out the math here. Because what we want to do is, as we talked about volts earlier, let's replace coulombs with this general unit. So that'd be kilograms. So that'd be force U has units of kilograms times meter squared per second squared times the unit. And by the way, we'll be using epsilon for this, for actually the rest of the series. So this notation is something to get used to because this is the entire basis of this notation. This is the entire basis of the series. So with that being said, let's take this and also recognize mass as kilogram, as well, having units of kilograms times meter squared over U squared. And then resistance. Let me just write everything down real quick. You'll notice that I have specifically placed the epsilons directly under meters, at least usually. This specific idea will become very important later on. But for now, we'll just stick to it being this way. Firstly, I would like to recognize that, again, mass U, if we replace this epsilon with charge, this becomes inductance, resistance U and gamma U. Resistance, so R sub Q, if we replace epsilon with charge or coulombs, this collapses down to resistance, so ohms. This mass goes down to inductance, resistance, and then 1 over capacitance, reciprocal of capacitance. Then replacing epsilon with meters or length, gamma. Gamma becomes the spring constant, R becomes drag, and M becomes just regular mass. However, let's also look at E equals QV. Well, U equals QV, which in this notation would become, energy equals U times F sub U. And we can see that here in the units. And interestingly, this works for charge, this works for meters. Eventually it'll work for magnetic fields. Well, not magnetic fields, gravitational fields, I'm sorry, mass with gravitational fields. That's what I was trying to say. But this should provide a basis that will work no matter what. However, let's see how this will work with electric fields. So we can find F equals QE, and, well, Q electric field, and the usual units here would be kilograms times meters per second squared equals coulombs times kilograms times meters per second squared coulomb. So with that being said, we can generalize these concepts a bit further. And specifically, we'll notice the difference in these units. That is meters per coulomb, meters per coulomb all squared, meters per coulomb all squared, meters per coulomb all squared, and meters squared per coulomb. We can rewrite that as coulomb meters per coulomb squared. And thus, from now on, we will be using F2U, M2 epsilon, R2 epsilon, and gamma 2 epsilon for these. And as far as the electric field goes, its representation would be force of, well, here, let's see. Yes, that'd be force of one charge. So force of one charge equals the charge times gamma of one charge. And of course, these are vectors, so we get to do this. And of course, there's not going to be objects for every single form of this notation, but that's okay. And as far as building up velocity and acceleration and all of that, we can go back up here and recognize that epsilon would become charge or length, velocity would become current, and this alpha, which is acceleration versus just regular A, becomes derivative of current, or it becomes just acceleration. So, with that being said, we can also look at the units for the electric field, well, for gamma 1Q, and notice that, well, yeah, for gamma 1Q, and notice that if we go for the integral of gamma 1Q by length, which is the electric field per length, we should get voltage, which is F2Q. And just to verify that, let us look at the units for that. That is kilograms times meters per second squared coulomb. For the electric field, multiplying that by length, we get this, and we can separate all this stuff out and finally get F2Q. So with that being said, we should probably recognize the general structure that we have here. We obviously have velocity and acceleration, and the regular unit, which is charge. The last thing we'll talk about is just showing the general structure. So we have energy in epsilon being kilograms times the unit squared per second squared times the meters per the unit to the nth power. Then force is kilograms times the unit per second squared, and this comes from work equals force times distance. And then finally we go down to gamma, meters per u to the n. And then we can also get R and M as, what is it? Kilograms per second, right. As kilograms per second, and per units, well, and per epsilon to the n, well, meters per epsilon to the n, and the mass structure would be kilograms per, well, just kilograms times meters per units to the n. Now, of course, not every n is going to be used. We can still use some of these n's, and eventually different n values of different letters will become applicable at different times. But for now, this is the end of this video. With that being said, this has been Ert, and I will see you in the next video. Goodbye, everyone.